So what we're going over today, okay, are the three parts of the Earth. We're going over mostly how they interact and a little bit of, well, actually quite a bit of heat transfer stuff. Okay, we talked about heat transfer in terms of thermodynamics in Unit 3. But we only talked about it from a standpoint of thermodynamics. It goes from hot to cold. We never looked at how it gets there. Today we're looking at how it gets there. But we're looking at that on a small as well as a global scale. So we're going to be looking at the ways that heat is transferred from one object to another. Obviously, we know it goes from the hot object to the cold object, or the hot area to the cold area, but we need to look at how does the heat move from one place to another. Okay? There are three means by which heat can be transferred. And you probably learned about them in like grade 7. Okay? Anybody remember what they are? 2 of them start with C, 1 of them starts with R. What's that?
Can you repeat the question?
What are the 3 ways that heat can be transferred from one place to another? Kind of has to do with what state they're in as well.
Convection.
Convection is one of them. Convection is how the bulk of it happens on Earth, because that's how energy is transferred in fluids. Okay, like convection currents, hot air rises, cool air descends. Okay, that's convection. All right? How does it move in solids? Kind of sounds like convection. Named after the person who takes your ticket on the train. Conduction. Okay, so conduction, okay, is how energy is transferred through solid materials. Okay, it involves that molecules collide with each other. Right, so they transfer their energy to each other by colliding. Right, and the last way is by waves. Starts with R. It's how energy gets here from the sun. Radiation. Yeah. Okay, radiation is any heat transfer by waves. Right. Okay, so we're going to look at how that works kind of on a global scale, what kind of things affect it, that kind of thing. So the 3 parts of the Earth are the Earth's atmosphere, the lithosphere, which is the solid or crust part of the Earth, and the hydrosphere, which is all the water on the Earth. These 3 things interact quite a bit to produce the patterns of energy transfer and weather and stuff like that that we see on Earth. Okay, we're going to look at how energy on Earth is absorbed, used, and reflected. So there's this trilogy theme today. Okay, there's 3 parts to the Earth. There's 3 ways that energy can get transferred, and there's 3 fates for energy when it arrives here from the sun. So everything in threes, okay, today. Okay, when energy gets here from the sun, 3 things can happen. It can be absorbed, it can be reflected, or it can be used. And by used, we mean this process. There is only one process that will directly convert solar energy into usable chemical energy, and that is photosynthesis. Okay, because we are talking about natural systems here. Okay, I realize that a solar panel can directly convert solar energy into electricity, but that does no good to anything but people. Right? The rest of the Earth cannot harness any of that. Okay, so we're looking at natural processes only. Okay. So first part of the atmosphere that we're going to look at is the first part of the Earth, the atmosphere, is what we're going to look at. It is by far the most important part of the Earth in terms of energy transfers from place to place on Earth. The reason for that, the atmosphere is the most fluid part of the Earth. Okay? Certainly the hydrosphere, which is made of water, is also fluid, but not as fluid as air. Okay? Air can move very easily and very quickly. Okay? And as a result, it can transfer energy from one place to another on Earth. Most of the time, that direction is from the equator towards the poles. But why would that be? Why would energy almost all the time be moving from the equator to the poles?
Because the equator's off and the poles are towards.
Exactly. second law of thermodynamics, energy flows from hot to cold. The equator is generally hotter than the poles. Certainly there are exceptions to that. Okay, sometimes we get really hot days and it's hotter here than it is, you know, near the equator, but in general, the equator gets more energy, so it's hotter there, and energy flows from the equator to the poles. All right, you're never going to be asked to know the layers of the atmosphere. I'm just going to quickly talk about them, but I'm never going to ask you about the troposphere or the stratosphere or the thermosphere or anything like that. Okay? We are most concerned with energy transfers. The bulk of those energy transfers occur in the lower atmosphere. So most of them in the troposphere, a few things in the stratosphere. Okay? We don't talk about anything above that because the air is so thin it barely qualifies as atmosphere anymore above that. Okay? So the troposphere extends to about 11 kilometers. Now, this is not a hard and fast border. The atmosphere is very irregularly shaped. We have this idea that the Earth is this ball, okay, and that the air around it is also a ball, except it's not, okay? The atmosphere is like all over the place, okay? There's different parts of it that are thicker, higher, whatever. Okay? It's a very irregularly shaped thing. So these borders that we're talking about here are just sort of general guidelines. Okay? So the troposphere generally extends to around 11 kilometers. That means that there are several points on the Earth's surface that you could stand where you would be outside of it. Okay? If you stand on any of the world's highest peaks, K2 and Everest in particular, you would be standing in the stratosphere. Okay? What does that mean for you?
Low oxygen.
Yep, so low that you'll die. Okay, there's a reason why the top of those mountains is in what climbers refer to as the death zone. Okay, the human body is simply not capable of surviving there long term, and by long term we basically need 48 hours or less. Okay, very few people have ever survived more than 2 days at that altitude. Okay, reason for that? There's simply not enough air pressure. It's not even really about oxygen. It's sort of about oxygen, but it's mostly about air pressure. There's so little air up there that the fluids in your body start trying to get out, okay? And you can actually drown. You kind of get pneumonia. It's called pulmonary edema. Okay? Fluid builds up in your lungs and you essentially drown, okay? Because there's not enough atmospheric pressure to hold the fluids in anymore. Okay? At that altitude, you can boil water at about 60 degrees. And so when climbers are making meals at like the last camp before they make for the summit, they eat their soup boiling, okay? And it's not that hot. It's about 60 degrees, okay? 65 degrees, something like that, just because the atmospheric pressure is so low. Okay? And so you can't really survive up at that altitude very well because you're just losing fluids like crazy. Okay? And it's very cold, and there's not a lot of oxygen. Okay? All of those things contribute. Same thing is true if you were to go to Mars. Okay? If you went to Mars and you didn't have a spacesuit on, what would happen? Yeah, quite horribly. Okay, you'd literally boil to death. Right? There's so little atmospheric pressure on Mars that there wouldn't be enough pressure to keep your fluids from turning into gases. Okay? What makes water boil at 100 degrees Celsius is the fact that there's a whole bunch of air pushing down on it. Okay? Atmospheric pressure, the weight of the air above. Okay? The less air that's above you, the less pressure there is, and the more likely things are to turn into a gas. Okay, that's why the boiling point of water gets lower and lower and lower the higher up you go. Okay? If you were on Mars, the boiling point of water is actually below the freezing point of water on Earth. Okay? And so, yeah, if you were to be exposed to the atmosphere on Mars, what little of it there is, you would boil, which would suck because you would pop.
Yeah, I could play
Worse, yeah.
That's funny.
You basically turn inside out. Okay? It'd be pretty awful. Because basically what would happen is all the fluids would turn into gases inside your tissue. Okay?
Oh.
It's the same thing that can happen when a scuba diver comes up too fast. They get the bends. Anyone ever heard of that, the bends? Okay? It basically means bubbles form in your blood. Okay? And when bubbles form in your blood, it can be very, very painful because they can get lodged in the blood vessels and then they expand and it's just pressure. It just pushes on your muscles. It's really, really painful. But if you were in a low atmospheric pressure environment like the surface of Mars or in the vacuum of space, you just pop. Okay? Everything just turns into a gas. And the worst part of it is you're conscious for most of it.
Oh.
Yeah, they unfortunately did studies, the Russians did during the space race on dogs. And it would have been pretty horrible.
So you would kind of like implode?
Not implode, because I would mean like collapse inward. You would explode.
Okay.
Yeah, you'd pop. It would be awful. Okay. It's right up there on my list of ways I don't want to die, like right under inhaling molten rock. I have a list. Ways I don't want to die. Those are right up there.
You need to hear that.
Okay. What's that?
You need to-
No, this is dark enough already.
No, come on.
Yeah, top five.
This generation.
Okay, slow painful death, like due to disease, that's like top of the list. I want that one. Inhaling molten rock, popping, yeah. Falling. It's not the fall that kills you, it's the sudden stop. But the fall it's the anticipation. You know you're gonna die. Something about that's really scary. Yeah. There you go. There's my dark list. All right. Because I used to like climb mountains and rock climb and stuff all the time. Then I had kids. I couldn't do it. I get up on mountains and I can't do it now. I'm too scared. I can't die. Kids. It changes you. All right. So stratosphere extends beyond that. Okay, about 50 kilometers. In the stratosphere is where the jet stream is. Anyone ever heard of that term? The jet stream? Okay. It's a high altitude wind, but it's an important mechanism for moving humidity and air masses around on Earth. And so that's where it occurs, and we'll talk more about that another day. And then the other ones, okay, they're much higher up. The only important thing that's in those would be ozone. Okay, the ozone layer is in the stratosphere, the upper part of it, and that obviously is an important gas for protecting us from the harmful radiation the sun spits our way every single day. Okay, without the ozone layer, ultraviolet light and other bad stuff, okay, would penetrate to the lower levels of Earth and fry us like eggs. Okay, so we don't want that. The other thing that's in the upper atmosphere, in the thermosphere and the exosphere, okay, is our magnetic field, or the Van Allen belts. Okay, they are basically just a big magnetic field that acts as a big giant energy shield straight out of science fiction that deflects gamma rays and X-rays and all kinds of other high energy particles away and around the Earth, okay, and protects us from those things. Without that, the Earth would be an irradiated wasteland. All right. So the atmosphere does a bunch of kind of important things, okay? As solar radiation comes in, all the bad stuff gets essentially blocked, deflected, okay? We have a big shield, the magnetic field around the Earth that keeps all that really bad stuff out, okay? Some stuff does get through, but it's the good stuff for the most part. Ultraviolet rays, in small amounts, they're actually good, okay? You need them to make vitamin D and stuff like that. So getting a little bit of that through gives you the healthy tan and gives you the vitamin D. We don't want too much, okay? But the stuff that does get through that's important is visible light, the stuff that we can see, okay? So the colors of the spectrum, and heat, okay? That's infrared radiation, okay? Infrared radiation comes to the Earth, and a few things happen. Some of the light that comes in hits the atmosphere and gets scattered, okay? Back scattered by the air. Right? Backscattering means that that wavelength of light, in this case blue, gets basically sent everywhere. Okay? What does that cause? Causes the sky to be blue. Okay? The reason the sky is blue is because the makeup of our atmosphere causes blue light, the wavelengths that are blue, to be scattered everywhere. Okay? And so the atmosphere and the Earth's sky appear blue. Okay? At sunset, the sky appears to be orange, red, those kind of colors. And the reason for that is, as the sun gets lower on the horizon, it travels through more of the particulates that are close to the surface, smoke, dust, things like that, and that scatters orange and red light. Okay? So at sunset, we see more orange-red sky because of that. If it's really dusty, okay, like really dusty days, the sky is a little bit more orange, has a more of an orange tint. That's because those kind of things scatter more of the orange wavelengths of light, okay, and make the sky appear slightly different color. All right, so some of the light gets backscattered. That stuff does not get to the Earth's surface, so it does not represent an input of energy. Okay, some energy gets absorbed by the atmosphere. If energy gets absorbed, what happens to the temperature? It increases. So anytime energy is being absorbed, temperature goes up. We're receiving an input of radiant energy. Okay, so that can cause the temperature to go up. Some of the radiation that doesn't get absorbed by the atmosphere strikes the Earth. That's when the three fates that we just talked about a few minutes ago can happen. Some of it will be absorbed. If it's absorbed, the temperature will increase. Okay. If it's reflected, nothing will happen. Okay? There's no decrease, there's no increase, it just bounces off. Right? Or it could be striking plants. Right? The Earth's surface is covered in plants. So this represents a fairly significant increase in energy because photosynthesis will take that incoming solar radiation and turn it into chemical energy, which is then food for the entire food chain. Okay, so those are the three things that can happen. Now, what do you suppose determines how much energy gets absorbed and how much energy gets reflected? On a hot day, what color do you probably want to wear? White. Why? It reflects light. Okay? White reflects all wavelengths of light. Black absorbs all wavelengths of light. Okay? So if you wear black on a hot sunny day, you're going to be hotter because it's going to absorb all of that solar radiation. If you're wearing white, it's going to reflect the solar radiation and keep you cooler. All right? You can try this at home. Just take a black object and a white object, put them out in the sun for a little while. Before long, you won't even be able to touch the black object. It'll be so hot. Okay? That is something called albedo. So the reflectivity of the Earth's surface is known as albedo. Your surface has lots of different colors, and all different colors reflect different amounts of light. So if we're comparing the Earth's surface summer to winter, the albedo is a lot higher in the winter time. Because remember, albedo is how reflective the Earth's surface is. So the more reflective, the higher the albedo. Right? So in the summertime, okay, the sun beats down on the surface of the Earth, and the surface of the Earth is darker. Dirt is exposed, plants are there, all that, rocks are exposed. Okay? 70% of the incoming solar radiation gets absorbed. Okay? About 10% gets reflected off of lakes and ponds and stuff like that, and about 20% gets reflected off of lighter colored materials. In the wintertime, when we're covered in snow, 85 to 90% of the incoming solar radiation reflects off the snow. Okay? This is why, part of the reason it's so cold is that whole latitude thing we talked about, right? The tilt of the Earth, the incoming solar radiation is very angled, and so it's not very intense. And whatever comes in, that very not intense sunshine, reflects off the snow. So we get very little input of solar radiation in the wintertime because what we do get mostly reflects off the surface. Okay? Now, we try and take advantage of this whole albedo thing in the wintertime. Okay? When we get a snowfall, what do they do to the roads? They put sand and salt on them. Okay? Now, our first thought is that, well, sand increases your traction, and there is an element of that. But the main purpose for putting a bunch of sand down on the road is to lower the albedo. You put a bunch of sand on the snow, and the snow is suddenly a lot darker. And it absorbs a lot more solar radiation. Combined with the salt, it melts a lot faster. It's also the reason why our roads here are dark. You go to other parts of the world, and especially like California, the roads are made out of concrete. They're much lighter in color. Because in California, if you build your roads out of asphalt, it gets so hot in the summertime that they'll get big dips in them. Okay? They'll get soft, and the trucks and stuff that weigh so much will actually make ruts in the pavement. Okay? I remember as a kid, we went to Disneyland, we drove down, my family and I, and we got a flat tire in the truck, and my dad tried to jack up the truck, and the jack sank into the road. Okay? It was that hot. Okay? That was back before they used when they still used asphalt before they switched to concrete. Okay? So we take advantage of that kind of stuff. Putting sand on the road lowers the albedo. It increases its ability to absorb solar radiation, which helps it to melt faster. This is also something they're very concerned with around here, with all the new coal mining that's being proposed okay, for the eastern slopes. I don't know if you guys have heard about that, okay? But they're worried about coal dust, okay? Coal dust is obviously going to be grayish black, a charcoal kind of color, and if that blows onto any of the glaciers, it will increase the rate at which they melt, because it will lower their albedo. Instead of being a pristine whitish blue color that reflects a lot of solar radiation, they'll become a darker gray color that absorbs more solar radiation and they will melt faster. Okay. Making sense? Okay. So all that stuff is related to this thing called albedo. So it's a pretty important concept. Make sure you know. All right. Other things that can happen to the solar radiation. If it reflects off the Earth's surface, we might not be done with it, okay? Some of it, yes, if it reflects off the Earth's surface, it's going to go right back out into space, and it's gone. We get nothing out of it, okay? But some of it will reflect back down. It gets up into the atmosphere and then hits stuff and starts to come back down. That stuff would be greenhouse gases. Carbon dioxide, water vapor, okay? Water vapor is a greenhouse gas, believe it or not. Okay? And the greenhouse effect will allow some of that energy to come back down, right? The greenhouse effect gets a really bad rap as being this horrible, terrible thing, but without it, the Earth would be a frozen ball, okay, of ice, and we wouldn't be able to survive here. We need a bit of a greenhouse effect, okay, in order to keep things kind of healthy and stuff here. Okay, so those are all the things that can happen to that, or that's kind of the role of the atmosphere. The role of the atmosphere is to transfer energy, okay, but also to allow some through and reflect some in the greenhouse effect and all that.
Is that what caused the ice age then? There wasn't enough greenhouse gas?
No, lots of things can cause ice ages, and they've been doing lots of studies on this. Some of it can have to do with the ocean currents. If ocean currents get disrupted or changed, then they bring colder water to areas that are normally warmer, and that can start ice ages. Another thing they've noticed is something called precession, and that has to do with the Earth's tilt. So the Earth's tilt is on average about 23.5 degrees, and the Earth's orbit is not completely circular. And so what can happen is, as the Earth is rotating around the sun or revolving around the sun, its axis can wobble back and forth. Okay? And when this cycle meets up with the furthest point away, so apogee, the furthest from the sun, if the northern hemisphere is pointed away when we're furthest from the sun, if that gets set up for a few, like 100 or 1,000 years in a row, which it can, that'll cause an ice age as well, because we'll get more ice forming in the northern hemisphere because there's less water in the northern hemisphere, and that can trigger ice ages. They've actually got a bunch of data that shows that ice ages always seem to happen when that particular alignment sets up, okay? And then as the Earth starts to tilt the other way, they go away, and we're starting to move that way, okay? So I'm not trying to say climate change and global warming are not a thing, they totally are, okay? But what's the cause of that may not be what everybody says it is. There's a lot of factors at play. Is some of it human related? Without a doubt. Is all of it human related? I don't think so. Okay? But that's up to you to decide. But there's a lot of science that says there's a lot of things to do with the Earth's orbit, there's a lot of things to do with ocean currents, and yes, there are a lot of things to do with pollution, okay, that can all lead to the changes that we're seeing now. Yeah? Okay, so this is the greenhouse effect. We kind of talked about that already. So energy can come in, reflects off the Earth's surface, or gets absorbed by the Earth's surface. The stuff that gets reflected can be bounced off the greenhouse gases back to the Earth, get trapped, okay, and we get a second chance to absorb that energy, making it warmer. Okay. Yeah. All right, hydrosphere. Okay. So the hydrosphere is all the water on Earth. Okay, that is water vapor, liquid water, and ice. Okay, it also includes groundwater, which is water that can be trapped underground for long periods of time. Okay, so all of those play a role in where energy goes. The ocean is what we call a heat sink. Okay, what that means is it can absorb a lot of energy and hold a lot of energy without changing its temperature very much. Okay, so a lot of energy can be held in liquid water. If there's a shift, like an ice age, like Mason was asking about, if there's a shift away from liquid water towards ice, that can cause big changes in energy transfers, because now as ice freezes, or as water freezes, its albedo goes up. Okay, it becomes more reflective. Its heat capacity, its ability to hold heat, decreases. Okay, ice cannot hold as much heat as water can. Okay, and it can disrupt the flow of energy, the ocean current thing I was talking about as well, okay, which can cause kind of a runaway effect, which is what we usually see in the fossil record and geologic record, is that as an ice age starts, it starts very slowly, and then it just kind of takes off and it goes. Okay? And similarly, when it goes away, we see a slow change, and then it just starts to take off, kind of like what it's doing now. Okay? We see those changes, and that's simply because of the nature of how much reflectivity there is, how much ability to hold heat there is, all of that. So the hydrosphere plays a big role in holding and storing energy on Earth. Not so much transferring, but holding and storing. Okay? It also plays a big part in the water cycle. As the water cycle goes through, energy travels through the water cycle. To evaporate water takes a great deal of energy. Okay? To evaporate water takes, what is it here? I'm drawing a blank on the number. It's several thousand joules per gram. Okay? To evaporate 1 gram, which is a milliliter of water, takes several thousand joules. Okay? It's big. And so when water evaporates from one area, that water vapor takes a lot of energy from that area to another area. So when that water vapor gets somewhere else and it condenses back into liquid water, it releases all the heat energy that was absorbed somewhere else. So it's a way to transfer energy from one place to another, okay? Especially from places like the equator toward the poles. Big moist air masses move upwards, move northwards or southwards, okay, from the equator, and they carry all of this special energy that we call latent heat with them. Okay, so that's another role of the hydrosphere, is to move latent heat around the Earth. Right. Okay, so within the water cycle, you're gonna have to know the water cycle again. I know you've been beaten over the head with that like 6 times already through your school career, but one more time. We still need to know the steps, but we look at the water cycle from an energy perspective, not so much the water perspective. Okay? Anywhere where we've got water changing state from low energy to high energy, so ice melting or water evaporating, we're looking at energy going in. Okay? Any place where we have the energy going from high to low, so that is water condensing or water freezing, okay? Energy is coming out and it's going into the environment. So in the fall, you may have seen this. If you see like a pond or a lake in the late fall, and it looks like steam is coming off of it. It is. That's energy coming from the lake and going into the atmosphere as the lake begins to freeze. Okay? So actually, the air above the lake would be a little bit warmer because energy would be flowing out of the lake, okay, as it changes state from liquid to solid. Okay. And similarly, when we get any type of precipitation, energy is being put back into the atmosphere, okay, as that water vapor condenses, or the water freezes if we get hail, okay, energy goes in. All right, so the parts of the water cycle, okay, remember evaporation, so that's water just evaporating from any water body. Transpiration is water evaporating from plants as they carry out photosynthesis. Okay. Precipitation is the water vapor condensing and falling back to the earth. Runoff, okay, is any precipitation that's not absorbed and goes in rivers and streams and stuff like that. Infiltration, I don't know if you guys have been taught that one before. Infiltration is when water is absorbed into the soil. Okay, so that can recharge aquifers and wells and things like that. Okay, that would be about the only new step. All right, questions there? Okay. All right, last thing about the hydrosphere, okay? Remember that this is about energy storage, okay? It can be about water storage as well, but it's mostly about energy storage. The ocean stores a great deal of water. Rivers and lakes represent very little because they're so small, okay? Glaciers represents a place where, again, energy is being absorbed, it's being taken away from other places and water is being put in, right? So this glacier here, and this is the Robson Glacier, and it is shrinking very rapidly, and that's because it's starting to get darker and darker. Okay? It used to fill that whole valley, and just over 100 years ago, in just over 100 years, it has shrunk lengthwise almost 2 kilometers. When we were hiking there, we got to a place in this meadow, and there was a sign there that said, in 1901, the Alpine Club of Canada marked this as the toe of the glacier. You couldn't even see the glacier from that side. Okay? But in 1901, that's where it was. Okay? And when I did this, it was 2003. Okay? So imagine where it is now. Okay? It's really receded. Okay? A long, long way. All right, we will leave it there, and we'll start with the lithosphere tomorrow. If you guys can clear off your desks, I'll come around and spray and grab paper towels.